So this meeting being recorded. Okay, good. So then we start to talk to each other, and I start to learn what he had been doing is this whole global poverty, and you will see quite a bit of today. But the basic I'm not gonna steal some here, but the thing is, like, what he was doing is essentially using deep learning models, deep learning, I shouldn't even say model, deep learning algorithms, deep learning something is there to connect the satellite image data versus the ground survey data. Okay, and he's going to talk a lot more about that. But at the very beginning, when Adel and we start to collaborate, Adel asked me, like, how do we can find more students to work on a very big project? I said, I'm a model, which is the AstroStack group. That's what we do, which is create a workshop. And then we, literally that's what this group do. Right? This is really workshop. So he knows about this AstroStack, from very beginning. And we initially thought about create another like AstroStack, this group. But then we start talking about more about the methodology side, because I needed to develop a new course, which is now the course taught. This is 30 year. That's 288. That's how it started with Adel. So two of us started to design this course, which some of you have heard me talk about multi-resolution. This was a multi-source, multi-phase way of thinking about things. And you will see today from Adel's talk that everything is there. So we just thought it'd be great. I was developing theory, and Adel had this wonderful, real challenge, global problem. So that's how the two teams get together. But we always wanted to connect it with this group, because what Adel's doing, I'm quite sure lots of technology there, methods there would be useful here. Mm-hmm. Essentially, is trying to using these, nobody understand why they're working, but the deep learning models, the CNN, connecting data from different sources to do prediction, try to understand. Now, for one thing, correct me if I'm wrong, okay? Adel asked me whether he should talk about causal inference. And I told Adel, like, astronomers probably don't really think about causal inference nearly as much as the social scientists. It's not like you guys don't do causal, you do lots of causal, but you have all the series. Causal inference, a lot of the things like doing really hard ones, I look at the data, trying to make sense of it. Am I right? The big causal inference, counterfactor thinking is not that big.
No.
Okay.
We rely on physics.
Can you see they have physics?
I love it.
Yeah. So basically, let's say what Adel trying to do is to create a database, a soft version of physics, right? Like Kano is here, there's lots of causal inference. So ultimately, everything we're doing here with two goals. One is to creating a database for other people to use, right? Which you guys do that too. The other is eventually is how does all the global poverty index, everything affects the policy making, affect people's lives. So there's a causal component, right? But that's why that was here, and I asked him to give a talk here. Of course, there's the challenge because everything he's doing is restricted on Earth, but he come up with a very beautiful way to connect and see how successful that is. Okay,
let's see how successful. Thank you very much.
Let's thank Adel. Thank you.
Thank you. That's a fantastic introduction, Zhao. It's really a pleasure. It's mine to have to work with you. So my challenge for this talk was really to find a connection between the work that we're doing in the lab and what you guys are doing. Fantastic work that we admire and seeing the news and beyond. And the way I spun this, as you have read the abstract, is through thinking about life in the universe. And we know there's one planet which has life on the universe, which is our planet, obviously. And so what we've been doing in this lab is really to think about ways of measuring living conditions. So is this okay? Yeah, let me remove this.
More.
There's a way to
Hit the more.
More? Okay.
Yeah. And then go down hide. No.
There you go. Okay.
Also, you can also get rid of that. So
Okay.
Sorry.
Hide floating leading controls. Control our shift.
This one?
No,
Okay.
no, next.
That's, yeah.
There you go.
All right, is this good?
Yeah.
All right, so if there are any
Yeah.
questions online, you please help me with those, as I will not be able to see
Yeah.
them. And I expect a lot of questions along the way. So the way I see this talk to unfold is really to think about life on the universe and life on the planet and ways that we can generalize what we are learning in the work with Jali in the lab with James and Connor and beyond. Is there any overlaps? Right. So obviously, we're still waiting for the moment where ET will show up. At least every time I have a hope when I read the news in the morning that there's going to be something on a breakthrough on that. But we're waiting. So the assumption that I will make in this talk and is really that I'll talk about ET as a fictional character, life in general, and living on planet X. I'll be coming to that in a moment in the way that sort of this talk is structured. And so my mode of argument is that what we learn by measuring life on this planet might to some extent generalize to measuring life on other planets. And the way that this measurement will happen will vary depending on the modes of data that you have access to. And this is a bit of the parallel that I'm thinking about. So again, I'm not a astrophysicist, nor am I an astrobiologist. Perhaps we can see the inception of astrosociology.
Why not?
I thought astrodemography would have been probably a better suitable term. But what it turns out that I was searching if that was taken, and Wikipedia found this on Wikipedia. There's actually a term for astrosociology. I've never heard of it. I thought I was the first, but here I am, 20 years late. I think it started some 2003. Someone started to sort of.
Well, thank you.
So I'm learning, learning myself. All right. So you might immediately ask, how can we take on this daring question? And as Jali explained in the beginning, that we've been working on these questions for quite some time now, right? So, although I'm the lead PI for the AI Global Development Lab, I really see it as a collaboration, as I mentioned yesterday, with multiple PIs, multiple independent researchers that are joining forces together to create something new, right? So the virtual lab that we're leading is a consortia of researchers here at Harvard, with James, Jali, perhaps others will join, with Connor in Texas, now at Harvard, and my collaborators and PhD students and postdocs in Sweden at computer science departments at Chalmers Technical University, and also at the Institute for Analytical Sociology and Linköping University. So we think about questions in the domain of global development, what's happening on the planets, how can we deploy tools to measure at the planetary scale processes that are important for sustainable development. In particular, we're focusing on poverty and health. And our interest revolves around, I would say, 3 areas: measurement, causal inference, and the joint of the two for applied research. This is a picture showing the team across the domain of disciplinary boundaries as well. So we have statisticians, computer scientists, as I mentioned, social scientists, and economists, and political scientists as well. So while we're waiting for ET to show up, really what my goal with this talk is to maximize transfer of knowledge of what we have learned and how that might be helpful in the future for measurements on Earth and other planets. We have n equal 1, so we are pretty confident in at least what we can say for this case. So the structure is really that I'm going to talk about measurement endeavors that we're doing in the continent of Africa. I'm going to talk a little bit about India as well, and these are we'll be showing you different methods as well of modes of doing this type of measurement of different outcomes of interest. I'll see how much time I do have, so you have to sort of keep track of me. I know there will be probably conversations along the way. I'll be focusing a bit more on the Africa results. If I have time to go a little deeper into the India results, I think that might be useful. I also expect you to stop me along the way. I think the email was highlighting that there would be a lot of stops along the way. So let's do that. I'm not going to focus that much on the mechanics of the methods. I mean, although I'm happy to talk about it, I think it's more useful to focus on, what the methods themselves can be used for. But some of the mechanics are obviously important. So if you have questions, feel free to jump in there. At the end, I'll have a heavier slide, 2 or 3, to think about what would it mean if we want to generalize our measurements to other planets. Okay, and so what kind of data do we need? How do we, do the measurements? And here I would really want you to join forces. We need to think about it. When I was flying from California, so I'm at Stanford right now at the Center for Advanced Studies. Flying from California, and here I was reading a totally different book, but my mind was percolating with this talk, and I thought, oh my God, I have all these really cool ideas about how to do these measurements on other planets. And I thought at some point, hey, maybe there is a commentary to be written on this topic. So if anyone's interested, maybe we can talk about it later. I mean, I'm not sure it's sort of fully fledged a research article, but some thoughts, lessons learned. Okay, so you let me know if it measures up those insights for that time of work. All right, so let's focus on Earth. What's going on here? So one of the critical things that we are doing in the lab is filling in the data gaps. Data gaps, why? Well, in order to study poverty and health and living conditions on the planets, generally speaking, not only on Africa, we're focusing on Africa for practical reasons, is that you need a lot of data. So what you're seeing here is a picture of the different living conditions that we see across the planets, right? So on the column side, you have access to drinking water with different levels of quality that we experience across the humanity. Different modes of transportation. Many people use their feet, and that's what we have been doing for 100,000 years before bicycles were invented, and so on and so forth. Between we were able to tame the horses or come up with inventions of bicycles and so on. So the modes of living conditions have several dimensions, obviously, right? So access to water, access to transportation, cooking.
I would say the second one actually is the most healthy one to the least healthy.
That's a really good point. So there is definitely a movement towards cars and now back again to cycling, right? So whether that's a good or bad thing, or even walking. See, James is taking the stairs most of the time when we're here, but not the elevators. Avoiding that, which is good for my body at least. Okay, so data, but we also know that the distribution of humanity, of people accessing different resources is hugely different. And we have many people living in level 4, including us, having food, water, and housing, shelter, and transportation served in the most highest quality way that we can experience. Obviously, there's variations within rich countries, but on average, we can think about people in the industrialized world living in conditions level 4. Level 1 is what concerns most of the policymakers when we think about poverty and health. Level 1, I mean, level 4 is where we think about also the environmental impacts of what we're doing. We're not in this talk going to talk so much about environmental effects, but really the critical aspect of what global development researchers as me and others are thinking about is that how do we push more and more people up the level ladder, right?
Now, I've seen this picture many times,
Yes.
but I actually never noticed what's a dollar sign there mean.
Yes. So there's this is the World Bank threshold of $2 per day. $8. So these are approximate thresholds of what it means to be poor or living in, I mean, in this graph is level 1 and 2 and 3 of sort of the middle range. These numbers are contested, I would say, in terms of a monetary perspective or monetary definitions, in the sense that the World Bank is focusing very much on income, whereas there has been a growth of thinking about more of the consumption side. What do we actually have access to, right? So $2 per day doesn't mean so much in terms of what food do I consume or what transportation do I use. Please.
Are there also quantiles? I mean, in some sense, I mean, are there like 25, 50?
Yes. So there is definitely ways of making this graph more fine-tuned towards the distribution of living conditions. So ultimately, in order to do that, and really what we want to do, there is a lot of income data. If you look at, the global scale, there is not as much in Africa still, as I'll show in a couple of slides. So what we really want is data at a high resolution, meaning that we want it to be temporally and geographically, the coverage of it to be large. So what we
But I
need,
guess it's not a quantifier there, another one, 45%.
Yeah.
But maybe like, did they, I guess when there's questions, like when the UN decided, they say the lowest is 10%, highest 10%,
Yeah.
is that some percentile?
yeah, I mean, it's interesting. The definition itself is more based on an absolute measure of what would it need. I mean, it's still arbitrary. It's basically a consumption basket that they have. So in order to have this consumption basket satisfied, to be able to buy, what would you need on average? And so they come up with this measure. But if you think about, say, totally jump into, say, the US, a different context, where we think about what does it need to be poor here. We then think about the 60% median. That's sort of a rough measure that is used, median income of whatever is done in terms of the distribution of incomes in the US. If you below that, that's then considered poor in the US.
Let me inject with you, sorry.
Please, no, please. Yeah.
That actually, through the work I learned from David Gordon, right? Was talking about the one challenge here. It used to be, because I do lots of surveys, it used to be we talk about surveys that you translate different language, you want to make sure, the same thing translate the same level, right?
Yeah.
Everybody understand. In this case, poverty is actually the other way around, because he was talking about, like, in a country like this, right? The question, for example, do you have access to internet? Could indicating you're being poor if you don't have this internet. But in other countries, do you have a table?
Yeah.
Like, so you actually want these questions worded very differently, but trying to capture the level. It's sort of, it's a survey question, design question. It's a kind of quite interesting. It's not keep the consistent, but keeps the meaning kind of considered, which is much harder to think about.
Yeah, I mean, in a way, you want to, in these dimensions, they're giving you some latent factors, if you like, of capturing these dimensions. But the way you capture, the way you measure them will be varied across the world. Now, the problem for us that want to create a harmonized data for the planet is that how do we pull that together? How do you utilize the data that exists so that we can think about the human species as one, right? So how do we think about that data set and that perspective? What we're doing in the particular area of focus in Africa is that we're thinking about these Y's being the outcomes, the data that we need. So however you slice and dice the data, you will still need a disaggregated labeled data set over the living conditions on the planet. The problem that sort of we are, as I was alluding to in the beginning, solving here is that because there is a scarcity of data and a lot of locations on Earth, and also historically, is that our aim is to create the tools and means to fill in those data gaps. And so currently what we are doing, and this is showing you some of the variation that exists using satellite imagery. Okay, so if we now turn, if we turn to a different data source, if surveys don't exist and aren't enough, how do we combine it with satellite images? And these are Landsat images from 1984, Cape Town. And what you see here is the change over time, the variation of visual variation that exists, that gives you information about the human species and what we are doing on the planet, right? The question is, how can we combine this data with what we know about living conditions, with computer science methods, statistical methods, to further the measurements of these living conditions on this Earth. Most importantly is also temporality. So if you would focus on this is Egypt, 2020 in Cairo, you see here that if you would only have a cross section of a data set, there's not much change. But if you look at the same period, 1984 and onwards, if you focus on this neighborhood, you'll see that in 1984 there was basically nothing there, but then built up over time. So that's an indication in that neighborhood stuff are happening. Human species are building things. And so the goal, and one of the critical goals in the project is to fill in the data gaps, as I was saying, where you have for countries like Burundi, no data in some time slice, but what you have almost always are satellite images. And so the goal here is to train a deep learning function, or several of them, so that you give it as an input the images, and out comes a estimation of living conditions. And so the end product data-wise is a data set, as I was talking to you about earlier. And with that data set, we can fill in the gaps. So again, this is Burundi, just one case. We're focusing on the whole continent and that time slice. But without our project, we will only be able to use two surveys, 2010 and 2017, from the demographic health survey. So these surveys are done in Africa and have been conducted since the late 80s, commissioned by USAID. So every country that receives aid from the US also enrolls in these survey programs. And so once you've trained this algorithm, you can now fill in the gap, and you get a series of time slices and data that gives you information about what is going on the ground. And so to be a little bit more specific about the training process, so here we're using the supervised method where we need ground truth data. And so the points here that you see are measured locations of those dimensions that I showed you earlier. And so we create this gridded map showing us living conditions in this locality. And the goal is to create that heat map to the right, where then we slice up these geographical points, where we can then train on the blue points and then impute or predict or estimate the living conditions in the red points, and outcomes then variety of information or graphs that shows us what's going on.
How do you identify this points initially?
The blue one?
Blue plot.
Yeah, the blue plots come from actual surveys done on the ground.
So you can send data.
Exactly. So for a supervised method, you need that to do that. And this will be, and as I will come into later, is that obviously if you would generalize this to other planets, that will be quite hard.
Mhm.
But what it turns out to be is that you could think about these surveys, those labeled data, is that either you have people going out to those localities to measure them, or you have some prior information about what is going on in the image, so you can label them manually without necessarily going there,
Mhm.
right? And so that's the way supervised method works, is that the more information you have, but you need labels, the better you can do. But that labeling will be sort of limited by the knowledge that you have for that image in that locality. But the good thing, sort of in our particular setting, is that we have a lot of these DHS surveys, actually for the whole global south. So we're focusing on Africa. The plan is to go at least cover about 60 or 70% of the global population. You can also think about other data sources that you can combine with, and this is where I'll be talking about in the India section of the presentation, where you can combine census data, survey data, maybe other types of data that we can triangulate to create these estimates.
Right, so the other question is, if you don't have this initial input, you cannot generate the new locations, which are locations of interest.
You mean the satellite imagery now?
Yeah, so if you start in 2009,
Yeah.
2011, you know that these are these blue regions which are interesting.
Yeah.
So do you include any new blue regions in the next?
Oh, yeah.
years?
Okay. So yeah, I see
And
what you
how
mean.
do do
So
that?
basically what we have here, so the model, as we were noting, so 2009, 11, we have training points for that locality. But we have also training points, for other time slices,
Oh, okay.
right? And so even for that, end result, so we have, and this is where there are some assumptions going on here. One is that you're capturing the time trend of living conditions by looking at whatever data that you have in those slices of time,
Okay.
right? Otherwise, if you only have, say, 2009 data in the beginning, and you're extrapolating up into the future, you're assuming that, there's sort of a stability in whatever you observe and that time slice is holding over time. Here we have several survey points, so even if there's change to that distribution, we sort of assuming to capture that by those new surveys.
Okay.
Yeah.
What is your spatial resolution?
The spatial resolution for the Landsat imagery is 30 by 30 meter.
Oh.
So
Down to a house.
yeah, so neighborhood basically, so it's like 30 meter, one color. Yeah, so a block basically, and we're using Landsat imagery, and I'll be coming to this in a couple of slides. Is that the Landsat has historical coverage and it's also publicly available. There are newer satellites launched in the past decade with sub-meter resolution that gives you really sort of even the car type that is standing inside of that on the parking lot.
But maybe the question was about the resolution of the poverty map.
That's also yeah, exactly. So the resolution of the poverty map is so several layers to that question. One is that the actual surveying is done face to face in a household. So there's a DHS surveyor going out, knocking on the door, having a questionnaire, asking about the living conditions of that particular household. Now, what happens is that you have I don't know if people online can see this, but basically you have a neighborhood where these samples are taken within some radiuses. These points are households, and they collect the GIS coordinates over the centroid of where these points are from. So they actually aggregate these numbers in the end. So it's a way of protecting privacy. And then what happens, and this is the paper that we've been working on with Jali and James and our collaborator Mohammed, is that what happens to protect privacy is that GIS point is some angle, random distance thrown away into another location. So that's a way of, if you like, injecting noise and reducing the precision of our estimates. And what we're doing right now in this first paper is that we can use some prior information and combine with multiple imputation to reduce that bias. All right, so this is showing you the availability of Landsat images. So Landsat has been around since the 1970s. The technology has been evolving, obviously, but I would say from Landsat 5 and onwards, the resolution has stayed constant. There are some added bands to it to measure different types of activities on the planet that are more environmentally related. Our work focuses mainly on the RGB bands to visually capture what's happening on the planet. We do combine it also with the nightlight imagery to see what happens during nights. There's a lot of research that happened in the past 2 or 3 decades where researchers were using nightlight information as a way of proxying economic development. So the idea here is that you have places that are, like Boston or New York, highly illuminated. Question maybe online? Maybe that was a muting issue.
How much do we know about the improvement of the satellite over the time? Other than, I assume the resolution is getting higher. Any other thing to improve the coverage or?
So for Landsat, there has always been one satellite orbiting
I see.
at a time. For the European Space Agency, launched 2014, there has been 2 satellites orbiting simultaneously. So the revisiting rates, 16 days, so 2 weeks approximately for each locality. Whereas Sentinel with 2 satellites, you can cover, about 3 days on average on each locality. With these commercial satellites, you can, the goal for some of them is to do several.
We can.
Leah, do you have a question?
Yes, it is, and it's like reference.
I think it's
I
a
think
few.
it's understood.
Maybe.
I cannot
Can you
understand.
mute everyone?
I sent a text.
Yeah,
to-
that's okay. So with these commercial satellites, you have, the goal is to do, within day measurements, so perhaps in the morning, midday and afternoon. Some of them have, these, what they call the Dove satellites. Basically, it's about this size and they have about 200 of them orbiting, creating a network of measurements over time. So really interesting products, that could be used, for measurement today, basically. But what we're interested in is the global development historically as well. But for moving forward, there's definitely for our project also a possibility of using those types of imagery.
I mean, I have a question for the Astro friends. Are these kind of data set you guys use at all? Is this completely useless to you guys?
No, this, you should be very familiar with GOES.
Which I don't, but
No,
I
No,
should.
no, GOES, right? I mean, this is the flare data that we've been looking at.
But this is different type of data, if we don't look down.
Yeah,
No,
but
we don't look down.
Yeah, that's what-
It's the same type of repeated.
Oh, yeah, no, that's right,
But
but
not from
but this
land.
particular one, you don't, there's nothing to.
Yeah.
Oh, yeah, no.
But there's a new satellite, temporal, which is looking at the Earth's atmosphere and looking at the pollution in the area, so it was just launched
Hmm,
last year.
I
And
see.
there is a center, CFA,
Hmm,
to analyze this data, so this is a new type of data.
right. Well, so how does it, what's the setup of that data collection?
I don't know details, sorry.
But it's mainly
Yes. It is,
atmospheric.
so, yeah, it's atmospheric and it has, I think it's combination of few satellites, so there was a Japanese version which was launched earlier, and then this is the American version, and it's all in collaboration, and we monitor the entire Earth, and it looks at the pollution, so it gets very good high resolution data.
That's a pollution.
Yeah, but I don't know details.
Yeah,
And
doesn't-
some, some
Okay. Mm.
elements. some
Okay.
Sensitivity to certain, specific elements.
Okay.
We have to learn more, maybe we need to have somebody from Temple. Talking here.
Yeah,
Because we
that'd
have,
be true,
yeah,
too,
we
yeah.
have people at CFA.
All right, so let me dive a little bit. So that was a bit of the data background. Let me dive into some of the results that we have for Africa. And this is mainly based on a paper that my PhD student Marcus Pedersen led and published in the proceedings of the Joint Conference for AI, a special track on AI for social good. So this is one of the early data products or methods that we have created and published last year. The main innovation there is really the time series aspect of it. A lot of these predictions have been floating around, but focusing mainly on cross section of data. And I'll be talking a little bit about how we achieve that sort of temporal architecture to capture that type of information. So as earlier said, Africa is the focus. We have about 60,000 DHS survey points. So these are cluster points. Basically, you can see them as a neighborhood level measurement as released to us, but we have household level information. So let me rephrase that. The neighborhood level GIS coordinate is what we have, but we have household level information about these outcomes that I earlier talked about. There are about 36 countries, and the time slice is about 30 years. And the goal is to see how well we can build this deep learning model to create the data set of interest. Please.
So do you see the data as a map or as a points spatial?
Yeah, I mean, we see it as a the end result that we've created is the 30 by 30 meter resolution. That's sort of what comes out of the model, but we could technically create a point estimate. So we could basically create a moving window of creating predictions at an even finer scale if needed or wanted. But the question is the quality of those predictions are still, we haven't evaluated.
So it's more like when I say map versus points, then it's like a map is like a field, right? There's even though you may not have an observation at a particular location, you can imagine that there exists an intensity that you're
Yes.
not observing.
Yes.
Estimating. Whereas with point processes, it's like there is a point measurement at one point at a location. And nothing.
Nothing else, yes. So I would say the outcome for the model are points, but our goal are maps, if that makes sense.
Okay,
It's actually a really good point.
No, it's a really important
Yeah.
because in old days, right, before the deep learning stuff, we always think about modeling as a spatial process, think about
Yeah.
drawing. But now this thing is just say, okay, to treat them as pixel values, dump this thing in it. Right, and then the effective, but actually, it's things should be there because the patterns, spatial collection obviously should be there.
Mm.
But I guess the actual when you implement to putting this CNN, that it actually has a pixel values for every locations, right? Because the satellite, even if it's
Yeah.
missing, it will give you some values there.
That's right. I mean, that's the interesting part of the
It's
deep
a
learning model.
mindless model process.
Is
right?
that these blue points that you asked me about are basically the points that we are showing on this map right now. Okay, so these are the points that there are training data for. So essentially, I don't know if there is a eraser here, but
behind the.
Under the,
yeah,
under.
just to give you a little bit more intuition about the input and output. I mean, basically what you have, you're limited by the resolution of the Landsat image, which is the 30 by 30 meter pixels. So the model itself needs that data set. I mean, these are the images, and then you have the resolution. I don't know if you see this, I'm standing in the way, but basically you have the resolution with 30 by 30 meter. Those points then sit on the center of that image, right? And so we have a scalar value of y's that the model is trying to predict. And what the model is doing is to find that mapping basically between the image space and that point space. So the output will be a point. But there's nothing, keeping you from, once you have the model trained, is to scan over new points, in whatever sort of range of the window that you want to move to approach a map, if that makes sense. What you will see here in our predictions, what we do, and this is purely because of computational limitations, but also sensible limitations, is that we do the predictions where we know people live. So we have another map, a human settlement map, where we sort of use it as a cookie cutter on top of the African continent and limits the predictions to those areas. Okay. So just to talk a little bit about the outcome variable a little bit more precisely. So what we have here is what we call the International Wealth Index. It's basically an asset index captured from the Demographic Health Survey. So each of those columns here is a questionnaire in the survey. And so if you would have a constellation of the following answers, you have a television, you have no refrigerator, no phone, and so on and so forth, you'll have a household IWI value of 12.73. So it's somewhere in the scale of 100 being maximum and 0 being absolutely off the chart. You're sitting here in this distribution, if you would answer like that, just to give you an intuition.
I'm curious, what is the utensil being defining here?
Yeah, so they have a definition of cheap utensils and expensive utensils. I mean, it's basically the quality of the utensils that you have in the kitchen.
That's a pretty expensive utensil. Do they need a cumulative?
I think cumulative. So here we would, we would probably not at this particular moment. Yeah.
Well, is that a utensil?
And if you would, just to give you, so the outcome variable varies between 0 and 100, and it's actually a PCA measure over these indicators. So I just wanted to give you a sense for what 0 and 100 means, and what happens if you change with or without television. You would go from 12.73 to 4, so you'd be sitting in the absolute bottom here.
Interesting, like if I don't have TV. for
But
example,
these days,
I
most
don't-
of us get rid of TV, right? We don't watch it. We basically
Yes.
have it.
So that's.
The cultural problems here, right?
Yeah.
Yes,
Yeah.
yes, yes,
It's a
yes.
hard
So
problem.
those questions and we found, yeah.
It's hard to be like, it's hard to come up with these measurements, you know, even for one country, right? It's hard, it's even harder to think about it time wise, and also these cultural changes that we're seeing, so.
It'd be hard to think about utensils for other planets. That's
Or televisions for other planets.
Right.
Yes, but this is what we have to handle on this planet, so just as a takeaway, what you need for ET.
So, yes, so, you know, this, bottom questions are, I think are more reliable, right? The drinking water, talking
Yes.
capabilities,
I agree,
flow, material.
yeah,
And
I-
steam. I think that's basically.
yeah. I mean, the way I see these is sort of indicators of, I mean, they are direct measures, but in a way, they try indirectly capturing the living conditions in the household, right? So although they might be off for, you know, some households on average, the idea is that they will be able to capture living conditions.
Office,
The number of rooms also depends on how many people there are in the household.
That's exactly right, and that will also vary.
Actually, very
culture.
density.
Then,
Yeah.
well, there is Jeff Scargill, comment in the chat.
Mhm.
In case you don't know about the NASA data visualization facility at Ames, close to Stanford, the hyperwall may be used for your research, and then there is a link to hyperwall.
Hyperwall, yes, if you can please, maybe if you put that
I
link
put
in
this,
a separate,
Yeah.
I'll look at it later, separate TXT file, please. Thank you very much for that comment. All right, so let's, we're building intuition here, right? So intuition about the outcome and what we do, you know, what we do on this planet, and, you know, if you want to do similar maps on other planets, what you would likely need to do it there. The satellite image data is really, again, the critical piece of the bands that we are relying on are the RGB bands. We have other bands sitting there on the Landsat imagery that we're working with, but also the nightlight bands that we add to our data. So that doesn't exist in Landsat, it's measured by a different satellite. And this particular paper, to handle problems of clouds, which is a recurring problem in Earth observations, is that,
that is also a common problem in astronomy.
okay, so you handle clouds on other planets, yes, so I figured, you know, clouds are becoming one of the more evil things that I'm thinking about, and I'm having my nightmares about clouds. Not only is it creating bad weather, it's interfering with our data measurements as well. So we need to create an anti-cloud party or something like that. All right, so I would say the 3-year median is, it's what we did in this paper. It's something that we're improving. I feel this is a bit arbitrary of why 3 years. There are seasonalities that are happening within the year that are, you know, perhaps important to capture, especially if you think about agricultural development or even fast-moving processes that happen on the planet. It could be natural disaster, it could be war and conflict. If you want to create data like this, you want to make sure that temporal variation is as high as possible as well. So what we want to do here is to capture slow and fast. Right now, we're stuck in this paper and capturing, I would say, more slow-moving processes. All right, and so what we're doing here is then slice up the temporal data into chunks of 3 years. So we call them these frames. And what we then do is that we create these deep learning models that are able to take frames as data. So the state of the art has been doing something like this, which is that it takes one single frame at a time. What we did, and this is the big contribution of this particular paper, is that we added what we call it's called a LSTM layer. It's a long short-term memory layer where you can link information that sort of comes down from the upper stream of the model And so the information of what happened in the past can propagate forward in time. So it's a fairly sort of standard way of sort of evolving things, you might say, but it's actually doing quite some of a difference. Please, the question.
Yes, I have a question related to these clouds and your 10 data points only. Can you use also the weather information for the areas? So it will give you a better resolution than just 10 images?
Yeah, so we do, I mean, we do have, because of the 16-day, approximately 16-day revisiting rates, technically we would have about 24 images per locality
Okay.
within a year. And we're doing this averaging, well, one, to tackle clouds, the second, to handle the massive amount of data that is thrown at us or available to us. So I would say this is a pragmatic decision that I would improve on today by, and this is actually what we're also doing, is that we are including that information to the extent possible. You might say, do you need all 24? That, will really bump up the computational demand. Can you use maybe one representative image of each season, maybe each month? These are choices that are to some extent substantively driven, but also a bit pragmatic sort of movement, which is sort of a signum of data science. Please.
I was gonna ask, so you mentioned that you have this population presence absence mask that you're applying, so that you can figure out which pixels you're actually going to train on because they have people there, and therefore you might have survey data. As people expand further out from cities, we saw this in the Cape Town example at the beginning. Are you changing this mask over time? And if so, what is this doing to your dimensions when you go to train on the data in this series manner?
Yeah, so really good question. So the mask, the human settlement mask, so that we apply at the sort of post-training, post-prediction stage. So we have already trained a model, we are confining ourselves to the DHS, which is just by necessity. We would wish we had more data points. So whatever is available to us in DHS, we use that. We train the model, and then we take truly out of sample, meaning that we don't have any labels. We now trusting the model and creating the data. At that stage, we apply the cookie cutter. Basically, we just focus on human settlements because we don't want to apply it for the whole continent, as that's computationally demanding. It's also insensible. If you predict in the Saharan desert, you'll actually get a prediction.
And that was non-zero probably.
And it will be non-zero, exactly. I'll show you some of that. It will, which gives you a sense for the model is always, it's like an autistic model. It's just doing what it's trained for, right? It's predicting between 0 and 100. We give me an image, I'll try to fit that prediction.
When you train, do you have zeros going in for the Sahara Desert?
We have not, but actually it's a really interesting idea of perhaps we need another class. So we're confining it to 0, 100, and it's sort of assuming that everything fits that universe, right? That line, but it does not. So if you would want a more realistic model, you would have to add another possibility of adding, like, this is a non-human settlements, and so I give you 0. If you want to train it to predict, and this is sort of now in the realm of semantic segmentation, is that if you want to predict deserts and forests and so on, you need labels for that as well for training. But it's a really important question. That sort of it shows you the limitations of training as well.
Yeah, just one thought about bringing this to the astrophysical realm. It would be interesting to apply the model as trained in other planetary contexts, just to see the model spits out. That could teach us something about, what are they paying attention to, what's not paying attention to.
Yeah.
So we should think about
One of the lessons learned that I'll be coming to is actually if you have, say that we discover populations and on planet X, ET discovered, whoa, but we want to know how are they doing? If you have no data at all, could we apply a model like this on top of it? And you'll see, yes, if some conditions are met. So obviously, if they are exactly like us, we could, if they use utensils, generalize it to that state. So I'll come back to that, but it's an interesting thought of what's the limitations. What do you need to do to capture life, to measure life on other planets, living conditions on other planets. Okay, so you let me know if I'm going too slow or if I'm doing well on time.
So what's the typical size of the overall data set or overall region that you look at? So do you look at the data always globally? Or is it, I mean, or is it just like regions? Because I presume what's probably very interesting is that, I mean, there must be regional correlations. And they can probably even reach far. There must not be local, right? I mean, there's, I don't know, I guess like, for example, the wealth index in Europe and US is correlated. For sure.
Yes.
I was wondering, like, okay, so what's the typical scale of correlations that is?
Yeah, so that's a really important point. As we will be validating the results, you'll see a lot of that geospatial correlation coming through. So you'll see that some countries that are closer to each other in terms of, you know, how the IWI is even generated, they will, as you said, will be actually doing similarly on the metric. So a lot of the probing of this, I would say, you know, training these models, obviously, you know, as a pain in the neck, because they're large and in scope and in size, but to probe how healthy they are, it's all about going down and looking where are the errors, where are we doing bad, where are we doing good. And as you'll see here in Egypt, where we have a lot of training data for, it turns out that we do pretty bad on Egypt. And interestingly, the problem there is that a lot of the data points, rich and poor on the IWI scale, are located on the same very dense area across the Nile. So it means that an image, it's really hard for a algorithm like this to separate out because of the size of the image being 6.7 kilometers squared, which is what we're using. It's probably too large to do that type of sort of differentiation of what's going on in Egypt. But that tells us a question that we've been thinking a lot about, Jolly, James, and I, and Connor, as to how to think about resolution in this instance. What's a proper resolution for the problem at hand? And I would say ideal resolution, and this goes, you know, intuition building from predicting if it's a cat or a dog in an image, is that, you know, you want the cat or the dog to be the center in the image, right? And so this becomes a centrality of how the attention of the model is working. But when you have something like a problem like this, where they're household and they're scattered, and, you know, the cat is in the background, it'd be hard for it to predict, right? So it's the same thing here. It's unclear for the model. It becomes a hard problem still, how the attention should be focused. So ideally, we want, you know, if I would wish how we can develop this method, is that we have household level pictures of just one household, right? Not a neighborhood, not the South Africa visualization that you saw, but for each household with a particular estimate, you know, and that will be going into the data. In way of separating out variation, if you like. Okay. Right. So deep learning wise, how? Yeah.
It's 1 o'clock, so.
Yeah.
If you can wrap up in about 50 to 20 minutes.
Yes, in 50 minutes?
50 to 20.
50, yeah, okay. So let me move on here a little bit just to see how are we doing, and this goes back to the question of generalization. How well are we generalizing across different modes of training? So what you see here is the out of area, out of country, out of time span. I'll explain these in a bit, but first, just an intuition how machine learning models are, in an ideal case, trained, because they train on IID data, right? So you have data that you train on, but you generalize new data that you assume distributionally wise, you know, comes from the same distribution, but you're generalizing to it, but the model has not seen it. So you're sort of learning and generalizing in a way that is dissimilar. Here we have issues of geographical and temporal autocorrelation, right? So there's that clear separation is not fully holding. So that's why we train it in different ways to at least sort of stress test the model of how would it generalize if the generalization set is set differently. So out of country and out of time span, are relatively self-explanatory. So basically, we're holding out, say, in Egypt, we train on the rest, we predict on Egypt, but there's actually several countries there. Same with time span, we train on a certain time, we hold out time as such. Out of area just means that there's a boundary of which DHS locations can overlap each other and not. And this, gives you a sense for the general performance of how much also frame. I mean, these are two the same model, just that it takes different amount of frames and simultaneously into the training set. Okay, but we achieve a performance of this is the person correlation metric of 0.76, which is, if you stand and think about it, that's pretty good. Like, what would say that an image can give you information about utensils and TVs and whatnot, right? But
Is this the R square?
this
or
is
the
Pearson correlation, yeah. Pearson
Correlation has a problem with, you could have a constant shift, it doesn't really.
Yeah, I mean, we did the R square, they're in the vicinity of similar numbers of between 0.75 and up to touching 8 R squared. Here, I think we also corrected for the sample mean in the data. Okay. So, in the interest of time, we have these sort of plots of showing a little bit of how well are we doing, where are we doing best, where are we doing worse. Break it down by rural and urban. You see that this is the IWI, the predicted, and then the overall wealth that we're doing. The rural areas is actually where our model is doing better on, because it's in a way better in separating out forest area and even settlement area. You have the by country results, and you can break it down also by the distribution of the IWI and see how you're doing better.
The by country results, I mean, so what does 0 mean?
Yeah, so exactly. So here, I mean, this is in terms of R squared, you can even get negative R squared. So basically, you're not doing better than the sample mean of prediction. And this is basically similar here. So if you have 0, you're not, doing any better than just guessing the sample mean on average on that sample. And as I mentioned, Egypt here is pretty much, in this vicinity here of the predictions. Okay, and the same for you can break it down. Where are we doing better in terms of the mean error improvement? And we see that actually where this particular setup is working better is in the end tail of the upper part of the distribution of IWIs. That's where the predictions are doing better. Okay. And also they're talking about deserts, and now we're thinking also about the mean squared error. And if we just visually, qualitatively would probe where are there less mean squared error improvements, and it turns out if you just select the areas of interest, I mean, I don't see any human settlements here. So this is most likely what has happened is that the DHS privacy protection mechanism is thrown out of the DHS point somewhere into the desert or a mountain. And there's not much information for the model to work on. Here, it's basically when it gets black, there's most likely missing Landsat imagery. Okay, just to build intuition, most improved areas where there's actual change. I mean, this is a little village, might be a little hard to see here, but you can see changes over time. This is Namibia, that was Morocco. Similarly, you focus on those urban settlements, South Africa and Egypt in this particular instance is doing pretty well. I mean, there's nothing there in the beginning, 1990, but there's something built. Validating the predictions, you might say, okay, so great, this is fantastic. What if you would use some other completely different data that might still have retaining information on the IWI score? And if you look at the Human Development Index, which is a UN measure created at the country level, so we aggregate the numbers, country years, and we see how well does our predictions measure up with the country level predictions, and you get a correlation metric of 0.5, which is reasonable. It's not perfect, but it's reasonable.
But I guess for me, this number doesn't mean much until I know how others have been doing so far. Like,
Yeah,
is
yeah,
this-
compared to others.
Yeah, like what's the current, what's before you work on this, what are the,
So
what
the,
people can achieve?
yeah, I mean, what we, in the previous slides, I showed the benchmarks of the different models. So the single frame was actually the state of the art before our model, which is the multi-frame model. So we're doing better, but it's, they did it somewhere in 0.73-ish. We push it up to 0.76. So it's sort of a horse race type of thinking. But we also do much better on certain time predictions, which their predictions are pretty weak on. Okay, so what comes out of this? Well, now we can create this data. So these are the maps, or the point maps, to your earlier question, that we have created using human settlements to cookie cut out the locations of interest. And now what we can do with these data, and what we show here to the right, are basically forecasting exercises of which villages would reach a certain IWI threshold by a certain year. And this is alluding to the policy side of the question of how many will be escaping poverty, and our estimates using the data that we've created are in this vicinity here. Bless you. So I have some results from India. I think I'll skip them completely and then just go to the lessons learned. I think that'll be more fun to talk about. Here, just to give you a big picture intuition takeaways, that we are doing similarly to what we did in the Africa model, but the problem that we're solving in the India setup is that we have different ground truths. So we have surveys from the DHS, we have census data, and the labels are not matching. And so how do you then train on something else and generalize on something other than that, using techniques called transfer learning? So you could transfer information from one distribution to another under certain assumptions. So I'll save that for later, and I'll just show them here so people can watch them. And we also disaggregate the IWI into different measures. I mean, we have about 90 different measures that we go over here and see how well can we generalize to many of these outcomes. I mean, some of these outcomes, and I mean, just now this is R squared, and this is the top part of the 90 list. Models, you see, we have everything from women are overweight. You're predicting that from a satellite image. That sounds pretty amazing. But really, you have to think about this sort of as a latent factor that you're capturing through other processes that happen in the image. That looks like a poor area that sort of correlates with living conditions as such. So I would love you to sit and meditate over this table, but it's in the Zoom recording, so you can do it later and we can converse about it. But I also want to show you where we do really badly. And for example, children aged 12 to 13 had received measles vaccine, for example. That's a question in the VHS, and we get negative R squared there as well. Okay. Again, we create data like this. One maybe interesting fact is to see activation maps. So basically, you've trained the model, and the question is, what in the model is actually prompting it to react, to create a prediction? So for the outcome permanent house, this should be the reverse. Blue means actually warmer, it should be red. But you see here, it's what is activating it. And we look at the RGB bands, and we see it's actually, human settlements that activates how the model is reacting to the information coming in to it. Looking at transport and motorization, we do see there is a road cutting through the image, and it seems to overlap nicely to the road in the image itself. So these activation maps are helpful for sort of probing the model to see, what is it actually reacting to. Okay, so I think this is perhaps the ending part, which is lessons learned. What did we learn here? I mean, what we learned is that we can measure living conditions through a combination of satellite imagery and some training data, right? That's sort of the big takeaway. So if you would think about doing something similar in the astrodemography discipline that I'm envisioning here, is what conditions do we, need to meet? I mean, obviously, they just get the first thing out of the door, which is really hard to do, would be impossible if ET existed, would be to travel there and ask them about their living conditions. Right, study that and see how well we can do a DHS survey or something similar, ask them about the utensils that they have, if they have TVs and so on and so forth, but it will just be infeasible because of the requirements of travel. So then we turn to something like a combination of using Earth observations, I would call it maybe planetary observations instead, obviously, and a combination of the machine learning methods that we presented here. Okay, so what assumptions do we need to think about here in this area? So, you know, another obvious takeaway is that ET has to live on the surface of the planet. So any ET that will be below the surface will be very hard to capture, right? At least ET has to leave some systematic footprint that is informative for what could be captured by a satellite image. Okay, so we, as we saw, humans need housing for shelter, we build transportations, roads, and so on and so forth. We cultivate the land, and that creates changes on the surface of the planet that is important to capture those traces of living conditions systematically. Okay, actually, one thing that sort of is implicit, but really critical is also how ET organizes society. So do they live in cities, or are they more secluded? So that although they might be many of them on that planet, they live very secluded areas, right? Basically sort of rural living conditions. That will condition the model. We need some technology that will be able to measure the surface of the planet's X. We are working with 30-meter square estimations. The night light imagery has the older one is about 500-meter squared resolution. It still yields information about economic activity on the planet. So if that will be possible, then you know we have a chance at using methods like this. I was doing some research, but could not really identify what's the best resolution of a surface capturing satellite currently, and even possibly. I know there are some physical limitations to what we can do. But I might, before I move on to the next slide, what hopes are there to create a technology like this that could measure, you know, a 30-meter resolution, or say maybe a 100-meter resolution, or a 500-meter square resolution?
Not
Milliarc seconds or better.
Say again?
Milliarc second resolutions are better.
Okay.
But you cannot even
Micro
protect the planets.
Yeah, right now, everything we have is planets as point sources.
Points.
One
Okay.
point.
1 point.
So
Okay.
that's, I was just thinking about that. So if you were to look at the Earth in such conditions, you would see patches of the Earth which are developed, patches that are not.
Mm.
So your signal is going to be a combination of these two. Right? So if there's a way to determine that, say that there are these two components, that would be major progress.
Okay. And these are satellites orbiting the Earth, looking outwards, right?
Yeah.
Yeah. So exactly. So that's cost-wise and also technologically wise what we can work with. Another would be to obviously send something closer to the planets of interest, but that will also be costly and quite difficult to manage.
And take a long time.
Take a long time, exactly. So this is sort of a compromise between how far or how close we can come to the planets of interest to capture activity.
Another possibility might be you could track variations over time. That might be, and then if there's ET on some planet that we happen to be observing for 20 years or something, then we could actually see if there was civilization changes.
Yeah. So I mean, just to give you a sense, if we had a satellite that would send from Planetex, if we would send a satellite, they're orbiting that satellite, what we need, at least just to give you a sense for the satellite, the data size that we're working in right now is about 15 gigabytes of data for the African satellite imagery, and about for the 60,000 households is about less than one gigabyte for the survey data, just to give you a sense for what information needs to be sent back to Earth, basically, if it would be set up in the similar way. The 30 meters squared data. So you have and 7 bands that we're working with. So you have considerably less if you can compromise a little bit, just to give you some fantasies. That's why. You're shaking your hand. This is not
It's
going
like,
to.
you know, sci-fi.
I know, this is the fun part of the thought. But if we do something like, say that we don't have, I mean, we still need images to actually do the predictions, right? Label data, there is some compromise with that, and this is sort of what I'm trying to get at here, but the images you need to order to, because that's the input to the model. So those are the critical pieces of information, and you guys do satellite images, so I'm hoping that I can inspire you to at some points to do that, assuming ET does exist and will exist. But doing what we were discussing, so if you would do exactly the same, you would need all that data to work out through. If you do something like a transfer learning approach, you would train on planet Earth, say, and you have a big model that is working pretty well on measuring what the living conditions here. And you could then transfer that, as is in the India example that I didn't go through that fully. You can get away with a smaller label data set, so you can fine tune the model to capture living conditions on that planet. Now,
But that's a very human-centric view, right? You're assuming the aliens will live like us.
exactly, and that's what I meant here by the distributions.
Yeah.
Are you assuming that the distributions on the conditional on the image space, the MX here, being the image from planet X, that conditional distribution
Doesn't change that much.
doesn't change that much. It's approximately the same. So if you have that assumption fulfilled, you can reason about it. Then you have a reasonable chance of doing something along these lines. You could use some supervised machine learning in the veins that Connor was suggesting, which I call risky business here, assuming that actually this equality does hold fully. Then you can transfer directly. Thank you. Yes. Then if you assume these distributions are actually equal, exactly what happens on Earth maps to the other planet, then you don't need to do any training. The only thing you need is images from that planet, and you'll be able to transfer our knowledge fully to that instance. You can also use unsupervised machine learning models that helps you categorize the living conditions on that planet, that would summarize that high-dimensional image space into what I would call here some low-dimensional labels that perhaps say richer or poorer ET living conditions that is helpful towards this task. But critically, as you see here, we need the images, and hence what I would like to one of the takeaways is that please work on the image side, assuming ET will exist for us at some point very soon. But what we overarchingly have done, at least for our planet, is to show that we can do this and on planet Earth. The question is, as I was alluding to what extent can it be done for other places? Okay. And so as I was preparing this lecture here, I was really thinking about, what else, can this be, as I was saying, the inception of a new unresolved list of problems, and there are unresolved list of problems on ET here specifically, but none actually on measurement of ET. So I thought, we need to add that to the Wikipedia page at least after this talk. So a big thanks to everyone here and also the team on planet Earth, but obviously we need to thank the satellites orbiting Earth, making this all happen. Unfortunately, Landsat 6 was killed in action, exploded on launch, but that happens as well in this business. Landsat 9 just joined 2-3 years ago in this endeavor, and interested in this work, please talk to me and Zhao Li, Connor and James. Check out our website, and a shout out for the Journeys of Scholars. It's a totally different endeavor, but also related, which is about interviews with esteemed scholars, and Zhao Li is one of them. Gary King at IQSS is another, talking about the meta conditions of doing research. Thank you very much.
I do have questions, but before I jump into that, are there any from Anybody here or anybody online? Probably not, so let me ask my question.
Oh, there's a question.
Oh, sorry, go ahead.
A few slides back where you were showing the predicted actual results, it looked like there were still some trends left over. And then that plus the map of Africa where you saw by country what the correlation was. Do you have a sense of whether it's like some countries that just have much better data than others, and that's why you have such better predictions for some countries, and like does that map back to your predicted versus actual graph where like those extra trends that are remaining are because some countries are just systematically not predicted well? Or
Yeah.
what do you think's going on?
So it's really one of the most important questions that we're thinking about when you're looking at that graph. What's happening in these countries? I mean, Egypt, I gave you an explanation why we're doing bad there. Another explanation is also the potential fast-moving processes that we're not capturing. So war and conflict is part, unfortunately, of the history of Africa, and we see a lot of that still happening. So there's some of that maybe playing in. That might not be the strongest, argument to explain everything happening in that trend. Another line of thinking here that is obviously requires more qualitative data and complementary data to verify, which is that the way that some countries sort of match their living conditions to what actually happens on the surface of the earth is different. That joint distribution is different. So the more sort of, just like an ideal case, the more, we build stuff, the more that matches to actually, we change how the satellite image will look like, that sort of correlates with growth, then the better you will do, the better you can use an image as a proxy. But if you build, I don't know, you build like just a bunch of statues, say, that doesn't, make a lot. It changes the image, but it doesn't yield information towards prediction, as we have some of the nightlight images, for example, from North Korea. You see, Pyongyang is like illuminated, but there's not much change over time. They're building statues and this is an example. So making it hard for the actual.
They have to do something different, right?
Other than the other stuff that happened in North Korea. Yeah, so I'm just think about it as a joint distribution where the image is a proxy of the outcome. And then how does that matching happen between the image and the outcome? If it's off, the image will not do a good job. Assuming that you have the right model, which is another sort of category.
I guess. Go ahead.
Oh, it's one thought. I mean, I think there's an interesting link here between the sociology and physics. There's a strong correlation between energy consumption and living conditions globally. So I wonder whether using that energy factor as a kind of conversion between the sociological and the physical would help us convert this over to the extraterrestrial domain.
That was gonna be my question.
That's a really interesting thought. So just to spin that a little bit, so how are you thinking about, do you have any ideas of how to measure it? I think that the answer is yes. I'm just thinking like, how can we measure that besides nightlights information? So you have any thoughts?
Yeah, I mean, I guess it would depend a little bit on the technologies being used, since every form of generating energy will have a different sort of signature in terms of pollution, in terms of heat, and so forth. So to some extent, maybe this would be brought by different modes of energy generation. But if there could be a kind of more general or universal way of capturing those signatures across a different range of technologies, since the ET might be using some super advanced form of technology that we haven't discovered, or they might be in the Bronze Age, or so if we can build a model across the different periods of that evolution of the society, maybe we can get leverage.
Industrialization as a predictor.
Yes.
Instead of how many, measles injections.
Yes.
That actually reminds me that Avi Loeb has been using this, right? Avi, you'll call it that he's the one who was like searching for this. But did they try to look at these? What do you call these? These are like a space trash or whatever the signals from these satellite. If they had a civilization, maybe destroyed.
At this point, as far as I'm aware, he's still only looking for fast moving objects.
that's what he was doing most recently, but I look at papers, basically trying to look at the signature from these, possibly civilization in the past get destroyed, but they may leave some things, like the moving in a second,
I mean, thing that comes to mind, it goes back to the atmospherical sort of question, is that if there is a lot of, I mean, at least industrialization, think about the carbon dioxide that has been emitted. This change in the atmospheric composition of chemicals is an indicator, at least. If you don't have high resolution imagery, but just detect the existence of ET, but you won't be able to capture variations within the planet, as it will be, evenly spread, more or less. But one other line of thought is, for example, oil extraction on our planet is often accompanied with certain heating signatures that might correspond to energy extraction, at least, maybe not usage directly. Thinking about I actually don't know the process of oil extraction, but there are these towers of burning gases, I guess, right? So there's like a clear signature of at least oil extraction that would not exist without that type of extraction. But I'm thinking about how can we measure it? I think it's a real terrific question, but how do we measure it on that surface of the planet? And that would be the crux of the problem.
One more question: do you have any way of dealing with prior information? For example, like something like a political system, I guess. So we should just come back to the North Korea example, or even just say like the ETs or communists, and then maybe the distribution is just constant.
Yes,
like in time and in space.
Yeah,
I like a song.
I actually thought about that particular example. What if ET would be highly egalitarian?
Yes, exactly.
Right. I mean, just like sharing a lot of. I mean, and then I thought, what would the signature of the city look like? I thought to myself, if it's highly egalitarian and also in the terms of, say, housing, right, how it uses houses and distributes, then you would see a more equal signature of how a city would look like in terms of height, say, right? And the distribution of densities, I would say, also would be pretty equal. If you think about the extreme case of full egalitarian ET societies. And that might, will not, directly correspond to. So the question is like, if you flip it, how would it look like if it was a dictatorship, right? I mean, if you look at the North Korean signature of night lights, it really, Pyongyang is the only city that is enlightened more or less at night. And I actually put in, but removed the slide. I thought was a little bit of a tangential point. But
that's actually interesting. First, I think we have a new sequel, ET movie, the ET the Communist. I'm sure this movie is gonna someone should work on it. But seriously, now we're thinking about just back to the Earth. Can we use stimulus to kind of show the political system? Because this is all about living conditions, right? Because I'm a dictator, right? Like, because there are some regions that I'm not dictator. So, well, look, the physical evidence is it just looks like it, it does like. Is that possible to do something on the political space? Why not?
I mean,
right?
also
Directly related to this, but I like the ET the communist. Just
Yeah.
an idea.
I mean, it's really as let's see if I have this. I mean, as we're talking about, I need to show you the images of it, but I think it could definitely be
It's interesting. A kind of a more physical evidence of dictatorship or something.
Yes, exactly.
But of course, we know there's lots of other evidence, but just sort of that historically, for example, can we historically to see?
It's not a bad idea. I haven't thought about it like that until I was preparing this talk. So I learned a lot thinking about on Earth.
ET,
Yeah, I mean, let me see if I can. Do you see this? Like I said, disappearing.
Oh, you just make the completely the constant.
Maybe it's like
okay, that must be it happens there. Yeah.
So you see this particular slide. So this is planet Earth night lights.
Right.
Okay, so this is how it looks like, and to your question, egalitarian ET, how would it look like? Well, I mean, it's really hard to see exactly, from this particular image, but I would say you would see more of an equal distribution of using land, assuming all land is usable, right? That would be like one takeaway, just looking at the US, that is not, the most egalitarian society. But if you look
Not
at,
yet.
no, that's exactly. If you look at North and South Korea, you see 1992, and this is 2008. You see basically Pyongyang, right, which is just sitting there, and you see Seoul is a huge, difference. It's a large difference in terms of how Seoul is developed, and Pyongyang, being probably one of the more extreme dictatorships on this planet, is basically looking like that.
Yeah.
Now, ET, yes, I think, to some extent, we'll see similar pattern, assuming similar distribution of how that system would play out. You would see something like this. But interestingly, if you look at countries, most human countries, there is a concentration of power still, right? The capital, the big cities will still be dominating, right? So that's
Literally the concentration of the power.
yeah, I mean, there's a concentration of economic power, cultural power, political power, and then we see also in Seoul. So we look at and say, they're building statues here, but not so much else. But here, there's a lot of activity. There's a lot of proud about what Korea has achieved. So, but there's a concentration of power towards Seoul, and you can clearly see that.
What year is the world?
The 2008.
No, the one.
I believe that is it's around 2000-ish, 10, something like that. Yeah. You think about something specific there, or?
Yeah, I was looking at the India map, and it's talking about concentration of power. That is, I don't think that's representative of what it looks like now.
Yes.
Because the Gangetic Plain has more people than almost China.
Interesting.
And there's right in this one, it looks almost dark.
Yeah. Yeah, and really, this is one image fitting into this particular screen, so you get like a lot of meshed up. If we do a high resolution night light, you'll see a better sort of what's going on within India. I mean, if you look at Africa, which is our targets, there's just not a lot of illumination here, except for South Africa. But that type of data has been used for the about 2-3 decades to measure income. We use nightlight in our models, as you remember, as one of the input sources, but we add the daylight component to it to boost the predictions. And if you'd only use this data, you would get an R squared of around 0.45. You add the daylights, you can boost it up to the numbers that we've shown, 0.7 and upward. Yeah, so it gives you some, food for thought about how we measure stuff here on this planet and how, potentially it could generalize to other planets. And it was really fun to compose this talk, at least for me, and I hope that you enjoyed this particular train of thought.
Thank you.
Thank you.
Thank you.
Well, the most important lesson I learned today is astronomers look up and we look down. That's the two differences. So it all depends on which angle you want to look at.
And I believe our next talk is.
We have a discussion with the students on
Yes.
Oh, shall you?
February 7th.
Yeah.
February 7th,
That's what-
right?
yeah.
You're gonna present something and we can
Oh,
discuss
yeah.
it.
Okay.
But I also reach out to the other students in the stat department and to see if they're prepared.
Okay. Bye, everyone.
Thank you. Thank you. Bye-bye.
And we still have one more